Hi, my name is Gokmen Tokkuzun and this is my VP Task 3. So the structure that I've chosen is found near a lake that's very close to a cafe called Waterside Cafe in Craigieburn. I initially chose it as it's a structure that I see often and it's quite unique around our area. So we started off with task 1, which was about selecting the structure, and after we conducted calculations within task 2 and also this final task 3. So these photos show dimensions of the structure and also labeled version of the structure A, B, C, D, E, and G. There was no F as we used that for calculating the reaction forces. The beams we analyze are AD and GE. So now moving on to the task 2 calculations, which were required for task 3. We analyze the beams by obviously drawing a detailed diagram. The first one, we used a UDL of 11.97 kilonewtons per meter, which was calculated by 1.33 times by my student number. And then we had all the dimensions and we had reactions at BY and CY. So we calculated the reaction forces by assuming it's an equilibrium. The sum of Fx equals 0, sum of Fy equals 0, and then we found the moment of B, and that should be equal to 0, the sum of it. And so by doing that, we found the reaction forces at BY and CY. Then I moved on. I used the next diagram to calculate the shear force diagram and the bending moment diagram, labeling all the points. I have the equations on the left-hand side and how I've calculated them. So first we found the equations for the shear force diagram, and then I used the areas of the shear force diagram to calculate the bending moment diagram. After that, I did the same thing for the beam GE. So instead of using the UDL, but we used a point load of 11.97, which is again calculated by 1.33 times by the last digit of my student number. Then we found the reaction forces by doing the same thing, and then I moved on to finding the shear force diagram and the bending moment diagram by calculating the equations on the left-hand side using the diagram in the middle of the page. So after that, we needed to find which one had the maximum bending moment and the maximum shear force, which was on AD. As we can see, the maximum shear force was 35.22 kilonewtons from the shear force diagram, and then the maximum bending moment was 42.78 kilonewtons per meter on the bending moment diagram. So after we found that, we could move on to maximum deflection and slope. So it was on AD, so we use AD, but to do so I needed the moment equation, and so this is how I calculated the moment equation. I had split the beam using x2. I calculated m at the very bottom for that section from B to C. And after I calculated m, I ended up with the equation. Then we know that the equation is equal to EI times by the second derivative of V, which V in this case is deflection. So to calculate the slope, we integrate it, have a constant of C1, and then we integrate it again for deflection, have a constant of C2. Then we have condition 1, which at point B, x is equal to 1.228, and v is equal to 0. Then condition 2 at point C, x is 7.112 meters, and v is equal to 0. So once we use those conditions, we can simultaneously solve for C1 and C2 as we have two variables and two equations. Then we end up with the slope equation and the deflection equation, which is EI theta is equal to the equation and EI V is equal to the equation. E is the Young's modulus of the material I'm using, which is steel, and I is the moment of inertia. So after that, we find the maximum deflection by letting theta equal to 0, which is the slope equal to 0, as we know that the derivative when that's equal to 0, then we have a maximum of the integral of it. So once we let the slope equal to 0, we solved for x, and we found x to be 4.17, and therefore the max deflection occurred at x is equal to 4.17. Then we substitute that in, and to find V max, we also need to divide both sides by EI, or times it by 1 on EI, to get V on its own. E is equal to 200 GPa for steel, which is the same thing as 200 million kPa. Then we calculate I of the beam, and then we can calculate the V max, so the max deflection. Then for the max slope, it's the same concept. The derivative is equal to 0, which is the moment is equal to 0. Then we solve for x, and we get two values for x, which falls between the required values. And if we substitute them back in, we get plus or minus 2.03 times 10 to the negative 5, which have the same magnitude, but they're just in different directions. One's going angled downwards, one's angled upwards. So after that, we find the bending stress and the shear stress. So the bending stress, we use the formula sigma x is equal to negative MYI. M is the maximum bending moment from the bending moment diagram before. And then Y is the centroid of the cross-section, which we can see at the top. Then we calculate I of the cross-section, substitute it all in, and we end up with a value of negative 9.507 MPa. Then shear stress, again, just using the formula. V is the max shear force from the shear force diagrams. A dash is equal to the area above the neutral axis of the cross-sectional area. And then Y bar dash is the centroid above the neutral axis, of the shape above the neutral axis. And then we calculate I the same way, and then B is the width. And then we substitute that in, and we get 0.587 MPa. Then we move on to stress transformations. For principal stress, we use the conditions of sigma x is equal to negative 9.507 MPa, sigma y is equal to 0, and tau is equal to 0. Then we find the principal stress sigma 1, 2 using the formula, and once we substitute it all in, we end up with 0, or sigma x, where sigma x is obviously negative 9.507 MPa. Then we can calculate the plane of theta p, and so tan of 2 theta p is equal to 0 when we substitute the conditions again. And then solving for theta, we end up with 0 and 90 degrees. Then we calculate the in-plane shear stress using the condition sigma x is equal to 0, sigma y is equal to 0, tau xy is equal to 0.587 MPa, which is what we calculated before. Then using the tau max formula, we calculate that tau max is equal to plus or minus tau xy. And then we find the planes the same way. Again, tan 2 theta s is equal to 0. So theta is equal to 0, or theta is equal to 90. So then we can summarize our key results with max deflection is equal to negative 2.145 times 10 to the negative 5 meters. Max slope is negative 2.03 times 10 to the negative 5 radians. Bending stress is negative 9.507 MPa. Shear stress is 0.587 MPa. Then for principal stresses, we have 0 or negative 9.507 MPa, and the failure planes of theta p is 0 and 90. And then the in-plane shear stress is plus or minus 0.587 MPa, and the failure planes of theta s are 0 and 90 also. Thank you.